Our method, which I presented in part 1 of this presentation, has been incorporated by Jan Ditzen in XT-DCCE2 using the option RC classifier. If you already have this command, you can check if you have the latest version by typing do update. Otherwise, you can download the command by typing SSE install XT-DCCE2. Okay, so for the purposes of illustration in Stata, we're going to estimate a simple model of banking risk where the dependent variable y is denoted as NPL. So this captures banking risk, in particular, the amount of non-performing loans expressed as a proportion of total loans for bank I at time t. And on the right-hand side, we have two variables, covariates. ROA captures profitability, so this denotes the return on assets for bank I at time t. And this variable is size, so that's the logged value of bank I's assets at time t. We have an example of 450 banks observed over 56 quarters. So N equals 450 and T equals 56. We're going to show that in the initial model, the rank condition is violated. And then we're going to see how to restore the rank condition using additional cross-sectional averages. So we're going to, let me jump into Stata. So we're going to control for latent factors using the CCE estimator. And to begin with, we're going to use cross-sectional averages of all variables in the model, namely NPL, ROA, and size. So let's see how to do that. XT-DCCE2. I'm going to add all cross-sectional averages. And then I'm going to add the RC classifier option. So here is a Stata output. So effectively, these are the mean group estimates of the slope coefficients. That is, the command will estimate the model for each bank separately, and then it will report the sample averages of the individual specific estimated slopes. So according to these results, the average effects are both statistically significant, with the coefficient of profitability being negative and that of size being positive. Therefore, on average, based on this results, it appears that more profitable banks take on less risk, all other things being equal, whereas large banks tend to take on more risk than smaller ones. Now, however, if we scroll down here, as we can see from the results, the rank condition is violated because the rank of C, which here is denoted by G, is less than the estimated number of factors M. So the rank of C equals 2, the number of factors equals 3, and the rank condition classifier equals 0. So as it stands, we cannot really trust these results because the CCE estimator is not consistent in general when the rank condition is violated. Therefore, what we're going to do is we're going to expand the set of cross-sectional averages in an attempt to restore the rank condition and thereby to control effectively for those 3 factors that are present in the model. Now, suppose now we have 4 other variables which do not enter the model directly, but they may still contain information about F. And these variables are ROE, which denotes the return on equity. So that is another measure of profitability. The second variable is called quality. So that is a measure of the quality of our assets. The third variable is debt ratio, which I think is self-explanatory. And the fourth variable is CAR, which denotes capital adequacy ratio. So we have 4 additional cross-sectional averages, while the rank condition is short only by 1. We could use all extra 4 cross-sectional averages. However, this risks over-parameterizing the model, meaning using too many cross-sectional averages relative to the number of factors. As it has been recently shown in the literature, CEG Karabik, Iodis, and Westerlund 2021, the use of too many cross-sectional averages can have a non-trivial effect on CCE, thus potentially distorting its inferences. Therefore, instead of using all 4 additional cross-sectional averages, it would be, my recommendation is to use the model information criteria developed in a recent paper by Margaritella and Westerlund 2023, and Karabik, Urbain, and Westerlund 2019. The objective of their IC procedure here is to identify which extra cross-sectional averages bring in new information upon F, the factors. Of course, the point here is that even if we find that some additional cross-sectional averages do bring new information, this does not necessarily mean that the rank condition has been restored. Therefore, the rank condition classifier should be run on the new or the expanded set of cross-sectional averages. So to run this information criteria on the 4 sets of expanded cross-sectional averages, we're going to invoke the STAT option within the XTDCC2 command of Jan. So I'm going to type STAT-IC, and then I'm going to include all 4 different sets of cross-sectional averages. So for reference, I'm going to start with the first set here, and then I'm going to do this 3 more times. So we have 4 sets, additional 4 sets. So let me type this here. And then in each set, I'm going to add an extra variable, starting by ROE, return on equity, then quality, debt ratio, and finally CAR. So effectively here we have 5 combinations of cross-sectional averages. This is the original one. And then we have 4 expanded sets of cross-sectional averages, each one containing an additional variable. So the XTDCC2 command will run the information criteria by Margaritella and Westerlund. And you can see that according to this criteria, the preferred set is the one that includes quality. So it appears here from these results that quality brings new information about F. Now let's see whether adding quality as an extra cross-sectional average is sufficient to restore the rank condition. Now to do that, we're going to click on model 3. So in that case, Stata will re-estimate the model using this extra cross-sectional average, and it will also report our rank condition classifier. So you can see here, this time RC equals 1. So the number of the resulting, the rank of the resulting Z bar equals 3. And therefore it appears that quality has been sufficient to restore the rank condition. In terms of the coefficients themselves corresponding to this new model, we can see that although the differences are not statistically significant compared to the original specification, the actual magnitude of the estimated slope of size is roughly 3/4 that of the original estimate. So the change is quite significant from an economic point of view. A natural question here is whether any of the remaining extra cross-sectional averages, even if they're not selected, would have been sufficient in terms of restoring the rank condition. So to check that, we're going to click each of the remaining models sequentially. So when it comes to the second model, where we added the return on equity, you can see that the rank condition classifier is 0. When it comes to model 4, adding debt ratio, again, the rank condition is not really restored. And finally, when it comes to model 5, adding CAR, this time the rank condition is restored. So in summary, the only other cross-sectional average that is able to restore the rank condition in this case is the capital adequacy ratio. Notice that if we scroll up to the IC, you can see that this was the second most preferred set of cross-sectional averages according to this criteria. In contrast, none of the remaining two additional cross-sectional averages are able to restore the rank condition. Now, if it would be of any help to provide some guidance by formulating the exercise we just did in steps, I would suggest the following procedure. So first, we run the standard CCE estimator and check whether the rank condition is satisfied or not using the RC classifier option in Stata. So here there are, of course, two cases. Case 1 occurs when the rank condition is satisfied. This implies that the CCE estimator is consistent, and therefore, in principle, no further steps are required. This is at least the case unless the number of cross-sectional averages used is way too large relative to the number of factors. Recall what we said before, that using too many CSAs relative to the number of latent factors can actually have a non-trivial bias effect on CCE, thus potentially distorting its inferences. So in that case, one can rerun CCE, but this time with regularized cross-sectional averages using the RCCE option, which is recently added by Jan as well. This option implements the approach developed by Yodis 2022. So the idea here is to use the singular value decomposition to remove the asymptotically redundant singular values of appropriately normalized cross-sectional averages. I'm not going to go through the details. You can read Arturas's paper itself, as well as the help file of the XTDCC2 command on how to use this option when the number of cross-sectional averages is large compared to the number of factors. Now, this was case 1. Case 2 occurs when the rank condition is not satisfied. In that case, CCE is not consistent any longer. So here what we need to do is we need to search for additional cross-sectional averages in order to restore the rank condition. To this end, one can use the IC of Margaritell and Westerlund for model selection on the optimal CSAs. It is important to check that the preferred set of cross-sectional averages is sufficient to restore the rank condition using our rank classifier method. Finally, it is worth mentioning that large heterogeneous Panel data models with latent factors can also be estimated in Stata using the command xtivdfreg, which has been developed by Sebastian Kriepfranz and myself. You can find videos about this command on my own website. Okay, so I hope you have enjoyed this session and the presentation has been clear enough. In the near future, I will try to create more videos illustrating other Stata commands. Thank you very much and good luck to your research.